What if I told you that the greatest empire in history was built not with swords but with shovels? We are accustomed to admiring marble statues and formidable legions, but Rome's true power lay underground and in the calculations of engineers. Modern builders, with their giant cranes and computer modeling, often lose out in speed to people whose only tools were a pickaxe and a plumb line. The roads we walk on today crumble after 5 years, while Roman concrete becomes stronger with each passing century. It seems like an impossible paradox, but ancient builders had technology that we still cannot fully replicate. In this episode, we will examine the mechanisms that allowed cities to be built in a matter of days and roads to be laid through impassable mountains. Watch the video to the end, and you will learn how ordinary volcanic dust allowed Rome to stand for thousands of years, and why modern skyscrapers can envy ancient amphitheaters. Guess how long it took to create this? We are used to imagining Roman legionnaires as warriors in shining armor who do nothing but fight barbarians. However, the reality of the ancient world was completely different and much more prosaic. For most of their service, soldiers did not carry a gladius or pilum, but a heavy pickaxe and a basket for earth. The Roman army was, first and foremost, a gigantic, perfectly organized construction corporation, unparalleled in history. Each recruit underwent rigorous training not only in fencing, but also in carpentry and masonry. The empire understood that conquering territory was only half the battle. It was much more important to develop it and connect it to the center. A tool called a delabra became a true symbol of Roman expansion, although it is rarely mentioned in films. It was a hybrid of an axe and a pickaxe, which every legionnaire carried on his belt next to his weapons. With the help of the delabra, the legions literally cut their way through the dense forests of Gaul and the rocky soils of Spain. The ability to quickly erect fortifications was valued by commanders no less than accuracy in archery. It was this versatile tool that allowed the army to be independent of the terrain. Soldiers could change the landscape beyond recognition in a matter of hours, creating a springboard for an offensive. Discipline on the construction site was as strict as on the battlefield. No one loitered idly, waiting for materials to be delivered or instructions from the foreman. Each centurion knew his task and clearly commanded his unit, turning 100 people into a single mechanism. The work was carried out in complete silence, broken only by the sounds of metal striking stone in short commands. This avoided the chaos and confusion that so often slow down modern construction projects. The absence of smoke breaks and long meetings sped up the process significantly. The Romans did not wait for ideal conditions or good weather to start work. If a swamp stood in the way of the legion, they did not go around it, but drained it or built a causeway. If there was a mountain in front of them, they dug a tunnel through it without dynamite or jackhammers. Engineering decisions were made instantly, and thousands of people immediately set about implementing them. This determination and willingness to do hard physical labor were the foundation of their success. They conquered nature with brute force, multiplied by precise calculation. The speed of road construction in border areas amazes even modern logisticians. The legion could lay several kilometers of a full-fledged paved road per day. This included cutting down trees, leveling the ground, creating drainage, and laying the pavement. Such efficiency allowed reinforcements to be moved with incredible speed. Rome's enemies often lost the war before the battle even began, simply because the Romans were where they were not expected. Infrastructure became as much a weapon as catapults. It is important to note that soldiers built these structures to last for centuries, not as temporary structures. They understood that not only they, but also their children would walk these roads. The quality of the work was strictly controlled, and negligence could cost the person responsible their head. A sense of involvement in a great cause forced them to work conscientiously. Engineering standards were uniform throughout the empire, from the sands of Africa to the mists of Britain. This created an amazing uniformity that simplified maintenance and repair. The organization of supplies also played a key role in the pace of construction. The legion did not just arrive at the site, it carried with it or produced on-site everything it needed. The convoy always included blacksmiths who could repair tools and carpenters who could build scaffolding. Clay was fired in portable kilns, turning into bricks right at the construction site. Stone was quarried in nearby quarries, which were developed by scouts. This autonomy eliminated downtime due to logistical failures. Even the officers took an active part in planning and supervising the work. Military tribunes and legates were often people with excellent engineering education. They could personally check the correctness of the road's slope or the strength of a bridge support. Knowledge was passed down from generation to generation through military treatises and practical experience. The intellectual resources of the army were enormous and were used with maximum efficiency. War and construction were inseparable concepts for them. This approach to work shaped the unique landscape of Europe that we still see today. Many modern highways are built directly on top of ancient roads, using their foundations. Bridges built by legionnaires still support the weight of cars. They are a monument not only to engineering, but also to incredible human endurance. Roman legionnaires proved that organized labor can literally move mountains. Their legacy lives on in every stone of old Europe. I would be very interested to hear your opinion on this approach to work. What do you think about modern construction culture compared to Roman discipline? Write about it in the comments. And be sure to subscribe to the channel so you don't miss the next episodes. Are you ready to learn the truth about what lies beneath the cobblestones? Roman roads were never just paved paths, as many mistakenly believe. They were complex engineering structures that went a meter or even a meter and a half deep into the ground. The builders actually dug a deep trench, which they then filled with various materials. The process was like baking a layer cake, where each layer served a critical function. Only this approach could guarantee that the road would not wash away after the first rainstorm. First, surveyors marked out a perfectly straight route, ignoring minor obstacles. Then the legionnaires removed the soil down to a solid base, creating what was known as the roadbed. The bottom of the trench was carefully compacted to prevent any future subsidence. The first layer of large stones, called statumen, was laid on this foundation. It served as a foundation and provided a reliable support for the entire structure. The stones were fitted together by hand with incredible precision. A layer of smaller gravel or broken brick mixed with lime was poured over the large cobblestones. This layer, known as the rudis, acted as a shock absorber and distributed the load. The Romans understood perfectly well that a rigid structure would quickly crack under the impact of hooves and wheels. The soft layer dampened vibrations, preserving the integrity of the top layer. This layer could be up to half a meter thick, creating a tremendous reserve of strength. Over time, the lime hardened, turning the embankment into a monolith. The next stage was the laying of the core of the road, or nucleus, consisting of fine gravel and sand. This layer was carefully leveled to create the correct profile of the roadbed. The center of the road was always made slightly higher than the edges, so that water would drain to the sides. The drainage system was thought out to the smallest detail, because water is the main enemy of any construction. Ditches were always dug along the roads to carry moisture away from the embankment. And only at the very end was the famous paving of flat stone slabs laid. These slabs, pavimentum, were hewn from the hardest rock available in the area. Their shape was chosen so that the joints were minimal and almost invisible. The wheels of the chariots rolled smoothly over them, meeting no resistance and not breaking the joints. Such a surface could serve for centuries without serious repair. Particular attention was paid to the curbstones that held the entire structure on the sides. They prevented the layers from shifting under the pressure of heavy loads and marching armies. Roman engineers built in excess strength, anticipating loads that did not even exist at the time. They built with a margin for thousands of years ahead, as if anticipating the future. That is why we still find these roads in excellent condition. The width of a standard Roman road allowed 2 carts to pass each other, which was the standard for logistics at the time. This ensured high traffic capacity for trade and military routes. Each section of the road had its own service stations and horse-changing stations. The entire system worked as a single organism, connecting the most remote provinces. The road was the physical embodiment of Roman order and law. Interestingly, the Romans even used construction waste from destroyed buildings for construction. Broken tiles and old mortar were put to use, reinforcing the middle layers of the road structure. This was an example of rational use of resources and waste-free production. Nothing was thrown away if it could serve to strengthen the empire. The construction economy was economical, but not at the expense of quality. Even in swampy areas, engineers found solutions by reinforcing the foundation with wooden piles. Thousands of oak posts were driven into the unstable soil, creating a reliable platform. Flooring was laid on top of them, and only then did they begin to form stone layers. These underground structures are striking in their complexity and labor intensity. The scale of the work was truly titanic. Today's technologies allow us to build faster, but rarely more reliably. We use asphalt, which requires constant renewal and patching of holes. Roman stone, on the other hand, lies motionless, ignoring time and weather. Do you think we are capable of creating something equally durable today? Or has the era of eternal things passed irrevocably? In the next chapter, you will learn the secret of a material that became stronger from contact with seawater. Want to know a secret that will change your perception of concrete? Modern concrete has one fatal flaw. It begins to deteriorate from the moment it hardens. Moisture-penetrating microcracks corrodes the reinforcement and crumbles the cement, turning buildings into dust within 100 years. However, Roman concrete, or opus cementitium, behaves completely differently, defying the laws of physics we are familiar with. It has the amazing property of self-healing and only becomes stronger when exposed to aggressive environments. Scientists have only recently unraveled the chemical magic that ancient builders possessed. The key ingredient in this miracle mixture was volcanic ash extracted in the Pozzuoli area. The Romans mixed this ash, called pozzolan, with lime and seawater. This triggered a chemical reaction that continued even after the solution had hardened. Rare minerals, such as aluminum tobermorite, formed inside the concrete. These crystals grew in the cavities of the concrete, strengthening its structure at the molecular level. When a crack appears in modern concrete, it inevitably grows, leading to the destruction of the structure. In Roman concrete, water entering the crack activates the remains of lime and ash. Recrystallization begins, and the crack literally grows over with new stone material. It is similar to how a living organism heals its wounds. This is why Roman breakwaters and ports have stood in seawater for 2,000 years. This material allowed the Romans to abandon the simple post and beam structures characteristic of the Greeks. Now they could pour huge arches and domes, creating spaces never seen before. Concrete took any shape that the wooden formwork dictated. This gave architects free rein, allowing them to realize their wildest fantasies. The Pantheon, with its giant, unidentified dome, is the best proof of this. The savings in using concrete were enormous compared to hewn stone. There was no need to search for, cut, and deliver huge monolithic blocks. It was enough to bring in crushed stone, sand, and lime, which were available almost everywhere. The work of mixing and pouring could be done by unskilled workers. This significantly accelerated the pace of construction of grandiose public buildings. The Romans also experimented with the composition of the filler to make the structures lighter. In the dome of the Pantheon, for example, light pumice was used in the upper layers of concrete and heavy travertine in the lower layers. This engineering solution reduced the weight of the dome and prevented it from collapsing. They had a keen sense of the material and understood how loads were distributed. Their intuitive understanding of structural engineering was centuries ahead of scientific theory. Concrete walls were often faced with brick or marble for beauty and protection. The internal structure remained rough but incredibly strong and monolithic. This created the illusion that the building was constructed entirely of expensive stone. In reality, Rome was a city of concrete hidden beneath a thin veneer of luxury. Pragmatism always went hand in hand with aesthetics. Surprisingly, the recipe for this concrete was lost for centuries after the fall of the empire. Medieval builders returned to stone and mortar, forgetting the technology of liquid stone. Only in modern times have we rediscovered the advantages of concrete casting. But even today, our Portland cement is inferior to its Roman counterpart in terms of durability. We have gained in setting speed, but lost in eternity. Roman engineers were not afraid to build directly in the water, creating artificial harbors. They lowered wooden caissons to the bottom, filled them with concrete mixture, and waited for the result. The mixture hardened directly underwater, forming indestructible foundations. This allowed Rome to dominate the sea with protected ports at all strategic points. The secret of Pasilan is a reminder of how the observations of the ancients can surpass modern technology. They used the power of volcanoes to create cities that would outlive the volcanoes themselves. If you like this fact about Roman concrete, don't forget to like this video. What if everything you've been taught about the impossibility of transporting water is outdated? The Romans faced the problem of delivering clean water to growing cities when local sources became polluted. The solution was aqueducts, artificial rivers flowing above the ground at bird's-eye level. The engineering audacity of these structures lay in their use of gravity alone. No pumps, no electricity, just precise calculations of the angle of inclination over hundreds of kilometers. Engineers had to maintain a slope of only a few centimeters per kilometer. If the slope was too steep, the water would erode the bottom and walls of the canal with its speed. If it was too gentle, the water would stagnate and turn into a swamp. Primitive but effective tools were used to achieve this precision. A mistake in the calculations could cost the city its life and the engineer his career. Aqueducts often passed through mountains, for which long tunnels were dug. Builders began digging from both sides of the mountain at the same time, moving towards each other. The accuracy of their meeting in the center of the mountain amazes modern surveyors. The discrepancy was only a few centimeters. This required complex mathematical calculations and perfect spatial orientation. Vertical shafts were made in the tunnels for ventilation and cleaning. When the path was blocked by a deep valley or river, the Romans built giant arch bridges. The arch allowed them to save material and withstand enormous loads. The famous Pont du Gard in France is a three-tiered bridge as tall as a modern 16-story building. The stones were laid without mortar, held together only by their own weight and precise fitting. It was a demonstration not only of technical power, but also of imperial grandeur. The water in the aqueducts was always covered with stone slabs. This protected it from the sun, dust, leaves, and, importantly, from poisoning by enemies. The city received cool, clean water suitable for drinking directly from the fountains. A system of purification tanks along the route allowed sand and sediment to settle to the bottom. Rome's sanitary standards were unattainable for most European cities until the 19th century. The maintenance of aqueducts was a separate, huge branch of urban management. Special teams of slave aquariums constantly cleaned the channels of lime deposits. If not removed, these deposits narrowed the pipe's lumen and reduced the flow of water. There were strict laws prohibiting illegal connections to the city water supply. Water theft was considered a serious state crime. The total volume of water supplied to Rome daily exceeded the consumption of many modern megacities. There was enough water not only for drinking, but also for grandiose thermal baths, fountains, and even flush toilets. This created a level of comfort that made the Roman lifestyle incredibly attractive. Barbarians who captured cities tried to preserve the aqueducts first. Engineers also used the principle of communicating vessels, creating siphons to overcome deep depressions. Pressurized water descended through pipes to the bottom of the valley and rose up the other slope. Lead or ceramic pipes reinforced with stone blocks were used for this purpose. These were extremely complex hydraulic structures that required constant pressure control. The risk of a pipe bursting was high, but engineers took it for the sake of delivering water. The aqueduct was a symbol of man's victory over the landscape and drought. It transformed lifeless plains into blooming gardens and allowed cities to grow indefinitely. Water became the blood of the empire, and stone arches became its veins. Even the ruins of these structures today inspire awe with their scale. Do you think modern engineers could build a similar system without using electric pumps? In the next chapter, you will learn how the Roman army built entire cities every night. The Roman army on the march was not just a moving column of people, but a mobile city. At the end of each march, no matter how exhausting it was, the legion built a fortified camp, a castrum. It was not a chaotic jumble of tents, but a carefully planned fortification. The legionaries knew their place and their task even before they stopped for the night. The camp was erected from scratch in a few hours on an empty site. First, surveyors marked out the perfect square or rectangle of the future fortification. Places were designated for the commander's tent, banners, warehouses, in each centuria. The plan was standard throughout the empire, so a soldier transferred from Syria to Britain knew exactly where to find his tent. This standardization eliminated confusion and saved precious time. Inside the camp, streets were laid out at right angles to each other. A deep ditch was immediately dug around the perimeter of the camp. The earth from the ditch was thrown inside, forming an embankment, an agger. On top of the embankment, a palisade of stakes was erected, which each legionnaire carried with him. The result was a wall capable of withstanding a sudden attack by enemy cavalry. All this was done by the hands of tired soldiers before they were allowed to eat or rest. The security of the camp was ensured not only by walls, but also by a wide clearing around it. The legionnaires cut down bushes and trees so that the enemy could not approach unnoticed. The firing zone was clear and visible in all directions. The camp became an island of order in the middle of the wilderness. Guards took up their posts on the rampart as soon as construction was completed. Strict sanitary standards were observed within the camp. Toilets were always located on the outskirts, at the lowest points of the terrain or downstream from the stream. This prevented epidemics, which often killed armies faster than enemy swords. Cooking areas were equipped to minimize the risk of fire. Discipline in everyday life was part of military strategy. If a legion stayed in one place for more than one night, the camp began to grow in infrastructure. Tents were replaced by wooden barracks and then stone buildings. Baths, hospitals, workshops, and even small amphitheaters appeared. Many great cities in Europe, such as Vienna and Manchester, grew out of such temporary camps. The street layout in the centers of these cities still follows the Roman plan. The speed with which the camp was dismantled was as impressive as its construction. At the sound of a trumpet, the tents were folded, the stakes pulled out, and the carts loaded. The camp disappeared, leaving behind only trampled earth and an earthen rampart. The legion once again turned into a snake slithering along the road to a new destination. Nothing of value was left for the enemy. This tactic allowed the Romans to feel safe in any enemy territory. They always spent the night at home, behind reliable walls, regardless of where they were. Psychologically, this gave them a huge advantage over the barbarians, who slept by the fires. Roman soldiers knew that their sleep was protected by engineering. The ability to quickly dig in saved many legions from complete destruction. In the event of a surprise attack, an unfinished camp became a fortress against which the waves of attackers broke. Shovels and pickaxes saved lives more effectively than shields. Engineering was the shield of the entire army. The Roman military camp is an example of the ideal organization of space and time. Efficiency was paramount, and every action had a purpose. It was a machine of survival, honed by centuries of war. What I am about to show you is banned in 12 countries as an example of cruel treatment of people. But at the time, it was the norm. The construction of the Colosseum, or Flavian Amphitheater, was the pinnacle of Roman logistics and project management. This gigantic structure was erected on the site of the artificial lake of the hated Emperor Nero. Engineers first had to drain the lake by building a complex system of drainage channels that still function today. The foundation was a giant concrete ring capable of supporting the unimaginable weight of the stone mass. The pace of construction was breakneck. The giant arena was built in less than 10 years. This was made possible by the use of the most advanced lifting mechanisms of the time. The Romans used huge cranes with pulleys, powered by the muscle power of slaves running inside large wheels. These rat wheels allowed multi-ton blocks to be lifted to great heights with remarkable precision. The site was filled with scaffolding, cranes, and thousands of workers bustling about like ants. The secret of speed also lay in the division of labor and the conveyor belt method. The stone was quarried in Tivoli, processed there, and transported as finished blocks. At the construction site, all that remained was to install them in place and fasten them with iron brackets. No one cut stone on site to avoid creating unnecessary debris and congestion. Delivery logistics were scheduled down to the minute so that carts would not cause traffic jams. The Colosseum was designed so that 50,000 spectators could enter and exit in 15 minutes. The system of 80 numbered entrances and staircases worked flawlessly. Each spectator had a token with the number of the entrance, row, and seat, just like in modern stadiums. The flow of people was separated, preventing crowding even when the arena was full. Social classes did not mix. Senators, citizens, and slaves had their own routes. Beneath the arena was a complex underground complex called the Hypogeum. It was a labyrinth of cages, corridors, and lifts for animals and scenery. With the help of a system of counterweights and winches, entire groves of trees or packs of lions could suddenly rise into the arena. The mechanics of the show were no less impressive than the architecture of the walls. This required the precise synchronization of hundreds of people working underground. The outer walls were faced with travertine, which was secured with iron pins. In the Middle Ages, these pins were torn out by looters, leaving the characteristic holes in the stone that we see today. The total weight of the iron used was estimated at hundreds of tons. This speaks to the powerful metallurgical industry that supplied the construction. Rome gathered resources from all over the world for this project. The Colosseum was also equipped with a giant awning, the velarium, which protected spectators from the sun. It was stretched by sailors from the imperial fleet, as controlling such huge sails required maritime skills. The ropes were attached to masts on the upper tier and controlled by a complex system of blocks. It was a prototype of modern retractable roofs in stadiums. Fleet technology served architecture. The building survived fires, earthquakes, and barbarian looting, but retained its structure. This is proof of the genius of the calculations behind the arch structures that distribute weight. Concrete, brick, and tuff created a light but durable skeleton, faced with heavy stone. Engineers perfectly combined different materials for different purposes. The construction was financed by treasures looted from the temple in Jerusalem. It was a political project designed to return to the people the land that Nero had taken for his personal palace. Vespasian built for the people, buying their loyalty with bread and circuses. Engineering here served as pure propaganda. Can you imagine coordinating the work of thousands of people without radios or telephones? In the next chapter, you will learn how the Romans came up with the standards we still use today. The Romans were the first to realize that uniqueness is the enemy of mass production and speed. To build quickly and in large quantities, everything had to be brought to a common denominator. They introduced strict standardization for bricks, pipes, and even wheel track sizes. This made it possible to produce building materials in different parts of the empire, confident that they would fit together. A factory in Gaul produced tiles of the same size as a factory in Egypt. Bricks had standard shapes: basalis, sesquipedalis, and bipedal. An architect could calculate the required amount of material simply by knowing the area of the walls. This simplified estimates and logistics, eliminating errors when ordering. Each brick bore the manufacturer's mark, which was a guarantee of quality. If a batch turned out to be defective, it was always possible to find the culprit. Lead pipes for water supply were also produced in strictly defined calibers. This made it possible to create complex branch networks using standard fittings and taps. Repairing the water supply did not require the manufacture of unique parts. Spare parts were taken from the warehouse. Such standardization accelerated the laying of communications in new cities. The engineer knew the capacity of each standard pipe. Even military tents were sewn from pieces of leather of a standard size. If part of the tent was damaged, it could be replaced with a standard patch without having to re-sew the entire product. This also applied to clothing, footwear, and cart parts. The Roman economy was the first mass production economy in history. Craftsmen became factory workers. The distance between the wheels of Roman chariots became the standard for road tracks. These tracks, carved in stone, dictated the width of carts throughout Europe for centuries to come. There is a legend that even the width of Stephenson's railway track goes back to Roman standards. Thus, the decisions of ancient engineers determined the parameters of transportation in the industrial age. The standard proved to be more durable than the empire itself. Standard building designs were used in construction. Baths, temples, and basilicas in different cities looked like twins. This was not a lack of imagination, but rather design optimization. Engineers did not need to reinvent the wheel. They simply adapted a proven design to the train. This saved months of work on drawings and calculations. Standardization also affected measures of weight, length, and volume. The Roman foot was the same in every province, which eliminated fraud and errors in construction. Trade and construction were based on a single metrological system. Scales and weights were checked by officials, and standards were kept in temples. Order in measurements meant order in the state. This systematic approach allowed the empire to digest new territories at an incredible speed. When arriving in a new place, the Romans simply deployed the ready-made matrix of their civilization. Wild lands were covered with a standard grid of roads in typical cities. It was a franchise of civilization that worked without a hitch. Large-scale production made it possible to reduce the cost of materials. Bricks and ceramics became affordable even for the middle class. The quality of life improved as things became cheaper and more accessible. Mass production was the key to prosperity. Roman standardization laid the foundations for modern industry. Henry Ford was not the first to invent the assembly line in standardization. He merely repeated on a new level what Roman foremen had been doing 2,000 years earlier. Roman construction was not just a gathering of people, but a clearly structured hierarchy of specialists. At the head was the architect, who was simultaneously an engineer, artist, and manager. Under his leadership worked mensors, surveyors, and liberators, levelers, who were responsible for the accuracy of measurements. This was an elite group of technical personnel whose knowledge was worth its weight in gold. An error in their calculations could lead to disaster. The main workforce consisted not only of slaves, as is commonly believed, but also of free workers and legionnaires. Skilled masons and carpenters formed guilds, the precursors of modern trade unions. They defended their rights, set prices, and passed on the secrets of their craft. Working in such a guild guaranteed a stable income and respect. The state often entered into contracts with such professional associations. Slave labor was widely used for the most difficult and dirty work. Slaves carried stones, mixed mortar, and dug pits under the scorching sun. However, skilled craftsmen worked in areas that required expertise. Slaves were not motivated to do quality work, so they were not trusted with laying arches or columns. Complex tasks required an interest in the result. The army had special engineering cohorts consisting of craftsmen of various specialties. Blacksmiths, armorers, and bridge builders were exempt from regular duties. Their task was to ensure the technical superiority of the legion. These people received higher salaries and had special status. Intelligence was valued and encouraged in the army. Work was organized in shifts so that the process would not stop for a minute. On large construction sites, work could even continue at night by torchlight. Foremen ensured that each brigade had a work front and materials. Downtime was punished with fines or corporal punishment. The logistics of people were as important as the logistics of stone. The Romans understood the importance of specialization. One person could not know how to do everything, so each person performed a specific task. Some only cut blocks, some only mixed mortar, and some laid mosaics. This increased productivity and the quality of the final product. Skills were honed over years of performing the same movement. Social mobility also worked on construction sites. A talented slave builder could gain his freedom and become a wealthy contractor. History knows examples of former slaves who became chief architects to emperors. The system encouraged talent and hard work, regardless of where they came from. Occupational safety was, of course, primitive, and mortality was high. But valuable specialists were protected as their training took years. Doctors were a common sight at large construction sites, providing assistance in case of injuries. The pragmatism of the Romans dictated the need to preserve the workforce. Huge masses of people were managed with strict discipline and clear instructions. There was no democracy on the construction site, nor could there be. The architect's orders were law and not subject to discussion. The vertical structure of authority ensured unity of design and execution. Thus, Roman construction was a complex social organism. It was a machine consisting of living people working like cogs. It was this organization that made it possible to implement projects that seem fantastic even today. How do you draw a straight line through a forest or mountain without GPS and lasers? The Romans had an arsenal of ingeniously simple surveying instruments. The main one was the groma, the ancestor of the modern theodolite. It was a cross with plumb lines at the ends, mounted on a pole. The groma allowed straight angles and lines to be constructed on the ground with remarkable accuracy. The surveyor looked through the plumb lines and gave commands to his assistants, who set the markers. A horubat was used to determine the horizontal level. It was a long wooden bench with a water trough on top and plumb lines on the sides. If the water in the trough was level, it meant that the surface was horizontal. This primitive water level was indispensable in the construction of aqueducts. With its help, they could detect a slope of just a couple of millimeters. To measure distances, an odometer was used. a complex mechanism installed on a cart. Gears connected to the wheel counted the distance traveled. Every Roman mile, a pebble fell into a special box, making a sound. At the end of the journey, it was enough to count the stones to find out the exact distance. It was the world's first taximeter. The diopter was a more complex device that allowed you to measure the angles and heights of objects at a distance. With its help, it was possible to find out the width of a river without crossing it. The Greek invention was refined by the Romans for practical needs. The diopter was used when laying tunnels to accurately align two faces. All these instruments were made of wood and bronze with jeweler's precision. They required careful handling and regular calibration. The profession of surveyor required a deep knowledge of geometry and astronomy. These people were the eyes and brains of any Roman construction project. The Romans also used sundials and water clocks to organize working hours. The day was divided into equal segments, and work proceeded according to schedule. Time was also a resource that needed to be measured and saved. Punctuality was part of the engineering culture. The rulers and compasses of Roman architects differed little from those we use in school. Every craftsman had a bronze folding ruler. Drawings were made on papyrus or wax tablets, and particularly important projects were carved in marble. The famous marble map of Rome, a detailed plan of the entire city, is an example of such documentation. Complex systems of blocks called pulleys were used to lift heavy loads. The more blocks there were in the system, the less effort was required to lift the load. The architect Vitruvius described these machines in detail in his treatises. Knowledge of mechanics allowed one person to lift a weight that would be impossible for a dozen people to lift. Tools were constantly being improved and adapted to new tasks. The Romans did not hesitate to borrow ideas from conquered peoples if they worked. Engineering thought was cosmopolitan and open to innovation. The main criterion was practical usefulness. Without these tools, however primitive they may seem, the greatness of Rome would have been impossible. The accuracy of measurements was the basis for the strength and beauty of their structures. Geometry became a tool for conquering the world. Why did they build with such fanaticism and dedication? For the Romans, construction was an act of civilizing chaos, of bringing order to the wilderness. Building a road or a bridge meant bringing law and culture to barbarian lands. It was a lofty mission in which many engineers and military leaders sincerely believed. Leaving a stone legacy behind was a way to achieve immortality. Emperors understood that grandiose construction projects were the best propaganda for their power. The name on the pediment of a temple or arch was read by millions of people for centuries. It was a way to legitimize power and demonstrate care for the people. Public buildings belonged to everyone, and every citizen felt part of a great whole. Construction united the nation. The economic benefits were also a huge incentive. Roads and ports accelerated trade, enriching the treasury and private merchants. Investments in infrastructure paid off handsomely through increased trade. Rome was the richest city precisely because of its engineering networks. Money flowed along the roads, just as water flowed through the aqueducts. For a simple soldier or worker, participating in construction was a way to earn money and gain status. After serving, veterans received land in the very cities they had built. They had a vested interest in the quality of the work because they were building for themselves. A sense of ownership was a powerful driver of quality. Roman law protected contracts and regulated disputes in construction. Clear rules of the game allowed businesses to develop and take on complex projects. The stability of the legal system was the foundation for stone walls. Engineers knew they would be paid if the work was completed. Even religion played a role. Many structures were dedicated to the gods, and poor construction meant angering the heavens. The consecration of buildings was an important ritual that gave construction a sacred meaning. Responsibility to the gods was higher than responsibility to people. But perhaps the most important thing was the sense of pride in belonging to Rome. Civis Romanus sum, I am a Roman citizen, sounded proud. The builders felt that they were making history, and this inspired them to great deeds. The greatness of the empire was their personal greatness. Rome fell, but its engineering legacy became the foundation for all Western civilization. We still use their terms, their roads, and their principles of law. They showed that humans are capable of changing the world around them on a global scale. Their ambitions knew no bounds. Today, looking at the ruins of the Colosseum or walking along the Appian Way, We feel a connection between times. It is a message from the past about the power of the human mind and will. Roman engineers defeated time, and that is their greatest victory. We have seen that the secret of Roman construction lay not in magic, but in iron discipline, clever logistics, and ingenious use of materials. They did not just build walls, they created a system that worked like clockwork. From the soldier with a shovel to the emperor with a blueprint, everyone was part of a single mechanism of creation. Their concrete became a symbol of their resilience, and their roads a symbol of their desire to move forward. Rome proved that a true empire is built on a foundation of knowledge and labor. The lessons of their engineers are still relevant today as we look for ways to build faster, cheaper, and more reliably. What topics from the history of ancient technology would you like to see in the next videos? Perhaps the secrets of the Egyptian pyramids or the Great Wall of China. Write your suggestions in the comments and be sure to subscribe to the channel to continue your journey into the past with us.